So should I start with the talk, or we
Yes,
wait a little
please.
bit more? Yeah?
No, let's get started.
Okay. Can I share my screen?
You have the
Yeah,
freedom.
I think so, yes.
Yes.
So can you see my presentation?
It's very clear on our side.
Okay, perfect. And can you hear me perfect?
Perfect.
Good.
Yes, yes, yes. Yes.
So I prepare a talk how to use machine learning algorithms, specifically supervised machine learning algorithms at big scales. And for that is needed to use, you can use different cloud computing platforms, but one of the most important is Google Earth Engine because it's focused to work with geodata, geospatial data. So my talk is going to be related with that. As I didn't know exactly the knowledge of the audience when I prepare the presentation, I'm going to introduce a little bit how we can work with Earth observation data or geodata, which is another name to call the Earth observation data. So for sure, first of all, we need data. There are different types of data, and we are going to see a few of them. We needed the algorithms, which are the machine learning algorithms, and we need infrastructure. In that case, the infrastructure can be our own laptops or can be a more complex infrastructure. So I have some knowledge, yeah, thank you. So focus on the data, we can find different type of data. In machine learning, the data is divided, is split in inputs and outputs. The inputs are the independent variables, which are the data that we are going to introduce in the algorithm in order to predict the outputs. So in our case can be, for instance, the reflectance values, the weather data, as for instance, temperature or precipitation. And usually they are raster or layers data. That is, can be images or can be geodatabases. And as output is the variable that we would like to predict, can be land cover, can be biophysical parameters as leaf area index or ground primary production or chlorophyll, depends the final project that we have. We would like to predict different type of biophysical parameters. Considering that we can use raster images, I put this GIF in the presentation in order to show you how the Landsat satellite acquired the images. And you need to consider that at the end, we have a lot of number of images if we would like to cover the global scale. So the blue colors in this case are 150 images, and the red colors are only one tile of the Landsat satellite. The average is around 70 tiles per area. So per year, so in order to cover all the wall, we use a lot of quantities of images in that case. For that reason, time to time, working in our own laptops is not manageable, produce the results, and then we need to use cloud computing platforms. We are going to see that in the infrastructure part. But before going to the infrastructure, we should focus in the different algorithms that we can have when we work with machine learning, because this is the specific part of the machine learning. Machine learning is part of artificial intelligence and computing science. And inside of machine learning, we can find the field which is called deep learning, which is focused on deep neural networks. So the main focus of machine learning is use the data and try to teach by commas the machines, the computers, in order to learn how to classify or how to predict specific outputs. And the way that is working, or they are working, is usually try to imitate the way that humans learn. When we are babies and we start to learn how to speak our own language, we need inputs, we need words in that language. And at the end, we can have output, which is the sentence that we can produce when we grow up. So the idea of the machine learning is doing the same with the computers. There are different types of machine learning algorithms. There are unsupervised, and this is related with the type of data that we have. If we don't have fieldwork, if we don't have ground truth, we focus on unsupervised learning, which is we only have the input data. We don't have output to teach the computers. There are the other part of machine learning, which is called supervised learning. In that case, we have the outputs in order to teach the algorithm to predict new samples, new pixels, new outputs. And there is also another part of machine learning, which is called reinforcement learning, that is focused more in near real time and learning learning from the outputs that the algorithms provide. So considering that we can have different type of data and we can use different type of algorithms, also we need to look in the infrastructure that we have. If we would like to train in an algorithm only using one tile of Landsat, we can use our own laptops. We can use also our PCs or laptops. But at the moment that we start to increase the quantity of data, we need bigger infrastructures, and then we need more complex platforms in order to process the data. And if we would like to try to predict or classify images in a global scale, we need to focus in the cloud computing platforms. There are a lot of geo cloud computing platforms. You can see here as an example, Amazon Web Service, Microsoft Azure, also Google Cloud, you can use it, or another more specifics or not so big companies can be, for instance, Sursara, which is a small company in the Netherlands that provide the servers in order to process the geodata. The problem of all this geo infrastructure is that we need to have a lot of IT knowledge. We need to deploy our process, we need to ingest our data, we need to know how to construct virtual machines in order to process our own data. To avoid that problem of the knowledge of the IT, appears Google Earth Engine in 2010. So this is a really huge platform, and it's an awesome platform in order to work with remote sensing and GIS data, because we don't need to worry in generate or create our virtual machines and install all the packets that we needed. It is already everything installed, it is everything prepared, and it is focused to the users that you can choose the data that you wanted, and you have different functions in order to classify images, for instance. As we commented before at the beginning, there is a GDE program. Nowadays, we are almost 30 GDEs experts in Google Earth Engine, and probably in the future is going to grow up the community. So keeping an eye in the program if you are interested to be part of it. The awesome part, I think that you are already Google Earth Engine users, so I'm going to pass more or less very fast in that part of the presentation, is that contains a lot of satellite images and a lot of GIS data, so it is quite awesome that there are temporal series from a high spatial resolution like Landsat or Sentinel to coarse spatial resolution that can be modest. And also you can upload your own data in order to process the data in the cloud. And the powerful of Google Earth Engine is that provides quite high computational power for analysis because it's a part of the Google Cloud. So you don't know that you are using Google Cloud in the moment that you are using Earth Engine, but in real, internally, it's using the Google Cloud technology. So we can use thousands of computers in order to analyze the data. You know that you can interact with Google Earth Engine in using JavaScript and Python applications. There are very, very small details that differentiate them. In the case that JavaScript is really easy because we can use the web development. We don't need to worry to install anything in our computers. But I wrote that it's limited processing. That means that there are some problems when you work with a lot of quantity of data because you are using your own browser. So the information or the data that you have in your script, which is user server, require the part of the browser of your computer. So this is the limited processing that has JavaScript. Also, when you try to process in a operational mode, whatever script, you have to click every time unless you look for install some packages. You have to click every time that you wanted to download one image. So it's a little bit uncomfortable in that way, but it's really nice to visualize the results, to see what you are doing and everything. So when I started with JavaScript. After that, I moved to Python. And nowadays, I develop toy examples in JavaScript. And when I wanted to do a operational mode or extract more results, I use Python. So this is the good point of Python, that is faster processing in the way that you don't use only the characteristic of your browser. You use your own computer, your laptop, plus the cloud for sure. And the problem is that you need to install the package and you need to install all the packages that you wanted to use in the processing chain. Here is a print screen of the JavaScript application. If you know, I'm not going too deep on it. Also, here is a print screen of Python application, which is a normal software in order to write in Python. In this case, it's PyCharm, but you can use other ones as Spider or other type of software to write in Python. And also, the good point of Google Earth Engine is that you can use Google Earth Engine in Colab, which is really, really nice because in that case, you don't need to install anything in your computer. Most of the packages, for instance, scikit-learn and also Google Earth Engine is already installed in Colab. So you can open Colab and you can start to write code in Python and run it on the cloud. So it is a good point of Colab. You can work in Python, but using the Colab application. What we can do with Google Earth Engine, we can do a lot of things, but we can have an image, we can have an image collection, and we can filter images by clouds, and then we can create a mosaic or a composite, and then we can extract different start of statistics. You can see here in this part of the slide the different type of functions that we can see or we can use in Google Earth Engine. And this part I consider really important. I mean, there are different types of objects in Google Earth Engine. We can use matrices, we can use arrays, we can use numbers, you can use data. But if you are working with geodata, if you are working with remote sensing or GIS data, the most important objects that you are going to use in Google Earth Engine are these four. EE.images, EE.image collection, which is a collection of images. For instance, one image is one acquisition of a specific area, and an image collection is a set of different type of images of the same area with different acquisition times. And in the case of the EE future, when you work with GIS data, for instance, with a save file, you can have one type of geometry, you can have a line, you can have one dot, you can have one polygon. That is the EE.future object. And when you are working with a set of different geometries, it is called EE.future collection. It is really important that because once you start to work with Google Earth Engine, you noted that there are different type of functions, as you can see in this part of the slide. You cannot use functions which are developed for future in the future collection because you get an error every time. And the same in the opposite side. You cannot use future collection functions if you are using a future. So for that reason, I think that it is really, really important to differentiate the four different type of objects, most focused to remote sensing and GIS data. So focusing in supervised classifiers in Google Earth Engine, first of all, I'm going to remind that supervised classifiers requires ground truth, requires fieldwork. You have to go to the fieldwork, and using that data, you are going to train the classifier. So this is the most important thing. You need to have ground truth. It's mandatory to go to the field? No, it's not mandatory. You can find ground truth because a colleague or because another research team or in another company, they have a ground truth. So you don't need to go to the field every time that you wanted to do a classification. But if you cannot find and you would like to use supervised classifiers, you have to go to the field in order to say, okay, this crop is potatoes, this crop are onion, these crops are whatever, are, I don't know, wheat, for instance. So there are two ways to add the ground truth in Google Earth Engine. One of it is the save files. I read it at the beginning. Now I cannot follow the chat because I share my screen. But I read at the beginning that there were some people working in geodata or GIS data. So I think that it's not needed to explain what is a save file. If you need it, you can ask later because now I cannot follow the chat, sorry. And another way to upload fieldwork data in Google Earth Engine is using CSV files, which is you can produce using Excel, the Excel software, so are not complicated. Once you have your fieldwork or in a save file or in a CSV, you can upload that one. For instance, this is a print screen of a CSV file that I had before, and I upload in Google Earth Engine. You click in the new, in the assets new, you click in the CSV, and then appears this menu. So only you need to select the files from your computer, and then once you select it and you click OK, the file should appear in this area of the menu. Once you have there, you only need to add an asset name, and that's all. You click in upload, and then the file starts to upload in the cloud. But there is two processes. First of all is upload. Second of it is ingest the data in the cloud. And once the data is already uploaded, you can see that you get the blue color in the task bar. And that's all. If you get the red color and you open the information, you will see which is the type of error that you get, and you should try to correct and do the process again. If you get the blue one, perfectly done, your data is in the cloud. So once you have your data, you can use different type of supervised algorithms in Google Earth Engine. I did it a print screen of the different types. Today, we are going to use the SMILE random forest algorithm, which is quite more or less fast. And then, yeah, it's not a really complicated algorithm, but you have easier algorithms as decision trees. You need to know that the random forest algorithm is an ensemble of decision trees. So in that case, you can create a strong algorithm, which is the random forest. And also you can find more simples, which is the minimum distance classifier. Is based on measure the distance of the data in a Euclidean distance and space distance. And also you can find more complicated algorithms, which can be support vector machines, which are algorithms based on kernel methods. And these algorithms, you lost the understanding what is doing the algorithm, because project the data in a higher spatial dimensions. So in that case, it's not easy to follow the explanation of the random forest. I think that someone asked something in the chat. No worries, I will ask all your questions when I finish these slides, almost done. And I will answer your questions, and later we move to the JavaScript Google Earth Engine to see an example of supervised classification. So the previous one were the different type of classifiers that you have, and these one are the functions that you can use once you have your classifier defined. You have to train the classifier, because the supervised classifiers requires to tell, I have my inputs, I have my outputs. This is the relations between my inputs and my outputs. That is the step of training classifier. Once we have that relation learning by the algorithm, we have a model, a classifier already trained, and then we can predict. The function predict you cannot see here. It's not predict the word. The function is called classify, and you cannot see in the ee.classifiers functions, because are functions that only can be applied to feature collections or images. So you cannot see the function here. We will see in the example later, no worries. But we can also use the confusion matrix function. Confusion matrix is a bit tricky function in the way that it's a bit confused at some point, because people consider that, oh, if I use the confusion matrix to my algorithm, I'm going to get the assessment of my algorithm in test. But no, it's going to be in training. And this is important thing also when you are using machine learning algorithms. You should try to avoid the classification results in the training subset, because the training subset is used in order to learn. So the classifier already see the samples before try to predict. So it's kind of a tricky, it's kind of a lie. No? If I know the word hello in Spanish, later it's easy to me reproduce hello in Spanish. But if you teach me Spanish and later I wanted to say a sentence in Spanish, I wanted to predict something in Spanish, I need to use words that I didn't see in my training step. This is what I wanted to say. The confusion matrix only works in training. We will see how we can get the assessment of our classifiers in the prediction step, and we will see in the example later. So now let's try it and let's see what's happened with a supervised algorithm. So I think that someone asked something. I don't know, where are you now? Yeah, here. Oh, you wrote a lot. I don't know which is the first question, but I think it's this one. What are some of the key challenges in applied machine learning techniques to geospatial data within the Earth Engine platform? Key challenge. If you are using supervised data, one of the key challenges is to have a nice ground truth of your data. And this is related with all the supervised classifications processing. It's not focused only in Google Earth Engine. The differences of Google Earth Engine to the rest of ways to classify or to make a supervised classification, that differences are in the programming language, in the way that you are using Google Earth Engine instead using pure Python, for instance. But the process of the classification is exactly the same than in another application or in another programming language. And I think that one of the key challenges in supervised classification is to have a nice ground truth, to have a good ground truth, a real ground truth. And in that case, for instance, one of the most complicated things is to have enough samples per class, which is an important thing when you are using supervised classifications. And your second question, Imad, is what are some common machine learning algorithms or techniques using geospatial analysis within on the Earth Engine ecosystem? I can tell you that the most common from the list that I saw are random forest and support vector machines are the most common classifiers. And you can find a lot of papers, a lot of manuscripts, scientific papers, focus on remote sensing data using classifications, supervised classifications, and probably you are going to find 90% of them focus on random forest and support vector machines. Nowadays, start to appear neural networks, but the problem is that neural networks are not really implemented in Google Earth Engine. In order to use neural networks, you have to move to the Google Cloud, and then you have to pay because it requires some cost. If you wanted to do it for free, without cost, you have to use Google Earth Engine, and in that case, you cannot use neural networks. More questions here. How can individuals or organizations get started with geospatial machine learning using Earth Engine, especially for those who have limited prior experience in the field? It's a good question. If you are a student in a university, I don't know if you are a student in a university, but if you are a student in a university, first of all, you have to register in Google Earth Engine. And I told you university because nowadays there are two ways to register in Google Earth Engine. I don't know if you have that knowledge, but the university's accounts, the research accounts are for free. If you are working in a company and you wanted to open a Google Earth Engine account, it's a bit more complicated because you have to do it paying if you open the account as a company. I think that the way to do it is if you, as an individual person, because if it is an organization, it's complicated, you have to pay probably, but you as an individual person, maybe you can open an account for free, telling that you would like to research or something like that. And to get started with geospatial machine learning, you can follow the script that I'm going to show you in a minute or 2 minutes, and then it's a good starting point to start to play with supervised algorithms. And also I can look you can look, sorry, for some YouTube videos also. There are a lot of YouTube videos focused on machine learning in Google Earth Engine. Michael, I don't know, Michel, I don't know how to pronounce, sorry. I think it's Michael, I suppose.
Yes, it's Michael. It's
Sorry.
Michael.
I have now a mix of German and English names. Sorry for that. Michael asked, can someone do prediction in Google Earth Engine? Yes, we will see. We will see how we can do that. What are some of machine learning models available for regression in Google Earth Engine? It's a good point. I think that all the list that I showed you, I'm going to share my screen again to show the different algorithms. Sorry, 1 second. Was this one? Sorry, presentation. These ones, all these algorithms, you have the function set output mode, and the mode can be regression mode. You have to write there in a string regression mode in capital letters, and then instead using as a classification, you are going to use as regression mode. More questions? There are not more questions. Is it clear? I think that I answered you all your questions, or I missed someone. Perfect. So let's go to the JavaScript. I need to share my screen first. Share my screen again. This one. Okay. Now I suppose that you can see my JavaScript. Can you?
Yes, we can see.
Okay, perfect. So this is a script that I prepared. I'm going to summarize a bit. This is the JavaScript, just in case any of you doesn't have clear. This is the JavaScript application. You can arrive there to using code.earthengine.google.com. And then you have here the scripts. You have here the documentation. For instance, here you can see all the classifiers, the same information that I provided you before. You have here all the information of the classifiers, the different type of classifiers. As Michael asked me, we can use set mode function. I need to scroll up in order to show you the information. And then you have to use this function in a classifier, and you can use regression mode. So in that case, classification is by default. Regression, you have to add regression in strings with capital letters. So I prepare an example. Sorry, this is the asset tab where you can keep all the results that you can get. You can export to assets, or you can export to Google Drive, or you can export to the Google Cloud. If you export to the Google Cloud, take care, because you are going to pay for that. But if you export here to the assets, it's not a problem. And if you export in your Google Cloud account, it's not a problem neither. Either. But if you export to the Google Cloud, take care because you can pay. Here is the inspector. That means we can go to the map and click in whatever point of the map, and you can see here that appears the results that I have already run it because I ran my script, and you can see the latitude and longitude that we are when I click it in the area. So this is the console, which you can see all the information when we get the errors and when we get we print the information that we wanted to visualize. And these are the task tab. In blue means that you already finished the task. Also, you can, if you export to the drive, you can open in Google Drive. You can see the source of the script that you produce the results. And if you see in gray, as you can see, it's because I cancel the task in the middle of the process for whatever reason. I decide, oh, I made a mistake. I cancel the task. And if you see here in red, for instance, that means that I got an error. Once you open, you can read the error and you can try to solve the error. There are some errors quite understandable, but there are others that no. For instance, that ones are quite understandable, but sometimes you get errors that you cannot understand. In that case, you have to go to the Google forum and then ask to the Google developers, okay? Because they can check your ID and then they can check what is happening with your error. But the errors like that are telling you this function is or expected array type or something like that is because, oh, I make a mistake. I use a function which is not to that object. Okay, so I can correct and that's all. It's not a problem. So this is the script that I prepare. Sorry. In order to upload the assets, you have here the new. So you can upload CSV or save files, as I told you before. So if you click, this is the menu that I showed you before, and you can follow the instructions that I put it in the presentation. And you can also upload your own geotiffs as the same, appears the same type of menu. You have to select the image in your computer, and then you can select the ID that you wanted and the name and everything, and then you can upload in your assets. So I did that with one table that I had here in Vienna. There is a agricultural area, and someone went to the field and did the field work, which class was each field at some point, and then I had that. First of all, I use a geometry, which is a square, which delimitate the study area. We can map in the map. We can add to the map in order to see what are inside of geometry. And if we run the script, I need to go to Vienna because the study area is there. So you can see that the geometry that I define is only a square in the study area. This is going to be the study area that I'm going to process. So I don't want to load all the wall of Sentinel-2 images. For that, I define this square. Okay, so this is the first point. This is the geometry. So this geometry is this one. Then after that, I'm going to load Sentinel-2 images. Sentinel-2 images are loaded in Google Earth Engine using this Copernicus Sentinel-2 SR ID. And in order to load an image collection, because it is an image collection, it's not only one acquisition image, it's all the acquisitions of Sentinel-2. You can go here and say Sentinel-2, and you can get all the information of Sentinel-2. For instance, this one. This one is the you can load the image, copy and paste this sentence here that I select, or you can type it in the script, and you can see Sentinel-2. This type of Sentinel-2 images are from 2017 until now, when there is not final date, is that are currently upload the images. So until now, so there are at least 5 years of Sentinel-2. It's not only one acquisition, it's an image collection. So for that reason, I don't write it, I don't type it ee.image, which is one type of object. I type it ee.image collection. So I'm going to use the functions here in the documentation. I cannot use the image functions. I only can use the image collection functions. So I only can use these functions. So this is really important, because if you use an image function in an image collection, you are going to get an error because are not objects for that function. So in order to not load all the word and all the year, I'm going to filter my Sentinel-2 image in a specific range of dates. The fieldwork was done in end of July or end of June, of 2007. So I'm going to load the images that fall in the period between 18th of June and 21st of June. And I'm not going to load all the Sentinel-2 image in that period of time, because if I upload the images in that period, I'm going to load all the wall, and I don't want to load all the wall. I only wanted to load in the specific area. So I'm going to use the function filter bounds. You need to have clear one thing. Filter bounds is not clipping an image. You are not clipping the images. Filter bounds, the things that is doing is go to the image collection and select the images that overlap the area that you select. But the images are not clipped. Okay? So the filter bounds are going to give me all the tiles that, even if it is very small part of the region, if there are a small part of the image that overlap with the area, are going to be in my image collection. Okay? And I'm going to filter. I used filter metadata, but I'm going to change because filter metadata is going to be depreciated. So I'm going to filter, and I'm going to use e.filter, which is equivalent to filter metadata, but filter metadata is going to disappear. So I'm going to do it well. I'm going to filter all the images in the image collection that follow all these properties, that the pixel percentage, cloudy pixel percentage, is going to be equal to 0. I wanted the images free of clouds. I don't want the images that contain clouds, because you know that in the optical range, the clouds disturb the information that you have in the image. And at the end, the clouds are noise in the image. We cannot see what are behind the clouds. So for that reason, I filter the collection, and I'm going to choose only the images that I have with 0% of cloud. If I run my script and I coming back to the console, you can see here, because I put it print image collection Sentinel-2 data. So the information of that output is this one. I can open it, and I can see that I only have one image there. Okay, so good. I have an image that I can start to work with it. You can see also that we have a lot of information in the Sentinel-2 images. The bands that start with B are the reflectance bands, but the other ones are different type of information that Sentinel-2 contain. So one of the things that I'm going to do is select specific bands. I'm going to select specific bands of Sentinel-2. I'm going to choose blue, red, green, red, the near infrared and red edges bands, and the shortwave infrared bands. Okay, so for that reason, I select these specific names. If you wanted to know the information, again, you can go back to the information of the data here in the search bar data, and then you can see here the description. First of all, you have the description of the data, and later you can see the different bands. So the band 1 is the aerosols. I don't want to use the aerosols in order to classify. I mean, these provide a lot of noise, and also the spatial resolution is quite low, so I don't want to use this band. But I'm going to use the blue, the red, the green, the near infrared, so on. So you can see here the information of the different bands, and you can select which ones you want to use, okay? So I did it that, and I'm going to select only these bands. In order to select the bands, I have my image collection here, and I can add select bands, and I can see the output that I have using print again. So let's look for that output, which is this one. And now you can see that we have an image collection, we have a features, only one image inside of the image collection, and now the bands are only the reflectance bands that I selected before. One thing that you need to have clear when you are using classifiers in Google Earth Engine is that you only can apply the prediction of the classifier in images, not in an image collection. I insist a lot on that because there are a lot of mistakes and a lot of errors always when the people start to work with Google Earth Engine. So this is an image collection. This is an image collection, and I just told you, because it's right in here, image collection, and I just told you that we can use only images to predict. So let's transform this image, because I know that I only have one image here. There is only one image. Let's transform this image collection to an image. One way to do that, because there are different ways to do that, is select the first image that we have in the image collection. If we select the first image in an image collection that only contains one image, it's going to select the image that we have. So I can uncomment this, and we can see that here now we have image, not image collection. So in that case, now we have an image. Now we can use this image in order to predict later. Okay, so we have here the different bands, and now it's not an image collection as before. Now it's an image. We can use that in order to start to work with the classifiers. This is first step. But as I commented you before, supervised classifiers requires inputs, which are the reflectance data in the images, and outputs, which are the ground truth. I have a table here that I upload in Google Earth Engine that is a table that contains different points, and in that points we have the type of class that are in that field. I use here in the print limit 2 in order to see what are inside of that table. Because if I don't put that limit 2 and I run this script, I'm going to get an error because I have more than 5,000 points. So in order to see what I have inside, you can use the function limit, and you can write 1, 2, 3, depending on the number of features you wanted to see. If you put it 2, 3, you can see 3. If you put 1, for instance, now we have 3 features here in the feature collection. If we put it only 1 here, we only get the first future there. So yes, we get only one future there. So if I open this in order to see which type of properties I have, you can see that I have a string attribute, a string property, water, a number property, because I codify the strings to numbers, because Google Earth Engine was with numbers. So you cannot classify strings. You have to use numbers. So you have to codify it. And there is a attribute, there is a property which is called training. I add this column in order to make easy my life in Google Earth Engine, and I assign ones to the points that I'm going to use for training my classifier, and zeros to the points that I wanted to use for... Is it a question? No?
Not a question. Not a question.
No question, no problem.
Yes.
And zero if I'm going to use the pixels for test my classifier. So I can load my table here, and I'm going to do that. Again, I'm going to change this because this is going to be depreciated. So I'm going to put it the correct function in order to not have problems in the future, because that function still works, but I don't know until when. So I prefer change this one to more current code. And then, yeah, are equivalents, but I prefer use this one in order to not have problems later in the future. I can filter, and I'm going to keep the samples that I'm going to use for training are going to be the samples that here in my training property is equal to 1. And I'm going to keep it in a validation, the samples that training is equal to 0, okay? So if you have questions, you can on the microphone, or you can type it in the chat, because if I share the screen, I cannot see your chat if you write at the same time. So once we have the training and the validation, you need to see the information that we have here. So let's print the first training. And if we print the first training, I think it's this one. I didn't put anything, so it's this one. This feature only contains 3 properties. But in order to tell the classifier the relation between the inputs and the output that we would like to predict, we have to have all together in the feature collection. So I cannot use this feature collection to predict, to train the classifier, because I only have the outputs. I need to have also the inputs at the same time. So in order to do that, I use the function sample regions. Sample regions is going to overlap the training points that I'm going to use here over the image that I have of Sentinel-2, and is going to extract the values of the image and put it inside of the feature collection. So doing that, you are going to get this. Now we have 13 properties, which we have the values of the image in that point and the properties that we had before in the future. This step is understandable because it's the important step in the classification. Someone asked, are you the one who prepares the feature table, or there is a source for them? Depends what you wanted to do. For instance, in this region, I had the information of the feature, so of the feature table, so I prepared the feature table. As a table, I'm not totally sure, but you can find land cover maps, and you can extract information from land cover maps and crop maps in Google Earth Engine. For instance, you have here, how is called, CDL in US. This one is a crop map from US at 30 meters spatial resolution. You can prepare your own table using some specific points and using this classification map. In Europe, there is a classification map too. I don't remember exactly now the name. I need to look, maybe Lucas, like that. Yeah, Eurocrop map is another crop classification map in Europe. For instance, I can tell you that, so sorry, but I never find in Africa a classification map of Africa that type spatial resolution, because Euromap is 10 meters and the CDL is 30 meters spatial resolution. But in Africa, I didn't find that type of maps. I worked years ago in Mali, and I create a classification map in one tile of image at 2 meters spatial resolution, but not more than that. Africa is one of the countries which has a lot of lack of information, and at least for European people, it's really complicated to get ground truth to create new classification maps. So at the end, you have to prepare your own table. This is the final answer to that question, because at the end, you have to prepare the table in order to classify the output that you wanted for your application, for your final product. So you have to have your own table. You can create in using different information, but at the end you have to do it. Perfect. So no one tell me that didn't understand that step. So let's continue a bit. And because we are in the main part of the script now, we are going to arrive to the classifier. So we have here our feature collection with the reflectance values and with the classification number in the attribute num class. We do that with the training set, and we do that with the validation set because we need to also to create that feature collection in order to predict in the test set. So let's define a classifier, because before training a classifier, we need to define the classifier. In this case, I'm going to use a random forest. The function of random forest in Google Earth Engine is ee.classifier.smile random forest. Random forest or smile random forest contains different inputs. We need to tell the number of trees that we wanted to use. I fix in 200 in this case. We need to tell the minimum leaf population, that is the minimum number of leaves, of samples that are going to be in the final leaf of the random forest. In my case, I select 5. And also we can select the back fraction, that is internally the random forest does a cross-validation. That's a cross-validation in order to select the features that are defined in each node and the threshold that are defined in each node. I don't know if you know how it's working a random forest, but in a fast way is you have different characteristics, different features in your table, different reflectance values. The random forest has to select one of them in order to start in the first node. Once you have the first one, has to decide the threshold in that feature in order to tell the samples that contains values higher than that threshold is going to one side. and the samples that contains the reflectance lower than that threshold value go to the other side. And it's going to grow up the tree until arrive to the final nodes. If you don't say anything, as a mean leaf population, the tree grows totally full. That means there is one sample in the end nodes. If you put it 5, for instance, here, you are cutting a little bit the tree, and that means that the final node has to have minimum 5 samples. And the back fraction is the number of pixels from your training data that is going to use to decide the threshold and the future. And the rest, that means 30, in my case, I put it 0.7. So the 0.3 percentage, the 30% of the samples are going to use to validate and decide which one is the best threshold and which one is the best sample. I don't know if that it is clear for you. Hope so. And if you have questions, ask. So this is the random forest. Once we have the random forest, we need to train the random forest. So we use the function training, and we use the samples training. And in that case, we create a model. This is the model. This is the classifier that we are going to predict new samples in the test set, in the image, in 1 pixel, whatever. We can get information from them. We can get the most future importance in the random forest, and you can print in your console using this function, using this chart, which is called chart. And you can see here that you have the different bands that the random forest uses, and you have there the different future important values. As higher value, most important future. As lower value, less important future. You can extract information from your random forest. But let's go to one of most important things that we can do and we need to do when we are making a supervised classification. As I told you, we have the confusion matrix. The confusion matrix is applied to the classifier. The classifier until now only show the training samples. So the confusion matrix here that you are going to get is based on the training samples. So you cannot use that as a final result of your classification. You can see here in my console, this is the confusion matrix. The confusion matrix is ordered by the classes. It's a matrix which are the classes times the different classes, and you can get the number of pixels that is classified correct. And if we are in the first row, which means class 0, the correct samples are in the column 0, and the wrong classes are in the other columns. So, for instance, in this case, in the training samples, we get good values for the class 0. But this is not the important thing for me. I mean, training is okay. It's good to know that I get almost 85% of accuracy in training. But the most important thing is what is the accuracy in a new samples, in a samples that my classifier never saw before in the training step. And in order to do that, first of all, we need to predict the samples in the validation set, which is the set that the classifier didn't see before. Once we have the samples predicted, we can open this future collection, and we can see that in this case, we have the reflectance values, the string name of the class, the number name of the class, the column training, and there is a new property which is called classification. This is the results of our prediction. And you can see, for instance, in this case, the classification is number 3 and our class is number 7. So it's not well predicted in this case. I choose one sample that it is not well predicted. But I can measure the accuracy of the classifier, and I can see the confusion matrix of the classifier. I'm going to close this. And This is the confusion matrix of our classifier in test, which is the most important results of our classification. And we get 71% of accuracy in our classifier. This is the good accuracy because you are measuring the accuracy in the samples that the classifier never saw before. This is only in samples that are dots in my map. I can show you that are dots in my map. These are the different dots that I use it to split in training and test. But I would like to have a classification map. I mean, I don't only want to have some classification pixels. In order to classify the image, we take the image that we define at the beginning here, at the top of the script. We take the image and we predict the image using exactly the same that we did it with the points in our feature collection. Classify image and using the classifier. In that case, we get a classifier, which is a classification map, you can see here at the bottom of the console, which is the classification map, is an image which contains only one band, which is the classification band. And we can plot it, we can visualize our results in the map. We can visualize our results in the map using this. First of all, I'm going to visualize my image, my Sentinel-2 image. So I'm going to not show the points. I'm going to visualize the image. This is the image collection in my study area. So this is the city of Vienna. I am here. And this is the agricultural area close to my place. So I can zoom in of the agricultural areas in order to show you that we have the river there, we have different agricultural areas, we can have also the vegetation close to the river, we have small towns, and also you can visualize the airport of Vienna here. So this is the study area, and I'm going to show you now the classification map that I get. I needed to, yeah, that it is here. So you can see in blue the river. You can see in red the urban areas. You can see in dark green the vegetation close to the river and forest areas that are in this area. For instance, you can note it here, there is a forest area there. And also you can, if I make a zoom in and I leave a little bit because needed a little bit of time to, is here, you can identify the different crops that we have in the image. If you are interested because, I don't know which is this pink color, I'm not sure what is that, I can open my inspector. I can click in my crop and it's going to appear here and it's telling me which is class 12. I'm not sure if I can, I have here ordered the different classes that I have from 0 till 14. So this is vegetables. So all the kind of pink color or skin color that you can see in the map are vegetables. Yeah, and that's all. I don't know if you have questions.
We have some questions.
Yeah, in the chat. Yeah. So how can someone avoid underfitting and overfitting training samples to machine learning models in Google Earth Engine? As the same than before, this is not only in Google Earth Engine, it's also in all type of supervised classifications. Depends the model. Depends the classifier that you're using. For instance, in the case of the random forest, one way to avoid overfitting is cutting the tree, is using a higher number of minimum samples in the leaves. Remember that in my case, I use 5. You can cut a little bit more the tree, and then the model is less complex, and as having a less complex model, you can avoid the overfitting. It's complicated in that way. This is a complicated task when you are working with classifiers, and everything depends on the data that you have, and depends the number of classes that you have. As much number of classes that you wanted to predict, your classifier is more complex. At much number of samples in the leaf nodes, the classifier is more complex, and it's a bit complicated. Another way that you can avoid overfitting is or increasing the number of training samples if you have the possibility, but you know that using supervised classifier, our main problem is to have ground truth. Usually we don't have enough training samples. So the other way is decreasing the number of samples. For instance, in this case, we did it a classification with 6, 8 reflectance bands, I think. It's not too much, it's not too high, the number of samples, but if you start to extract information, if you start to calculate vegetation index, if you start to extract spatial filters and so on, you increase a lot your number of features in your data. And then that using a lot of features compared to few number of training, you can fall in overfitting. So another way is making a feature selection method, or applying a feature selection method, or applying a feature extraction method in order to reduce the dimensionality of your data. That are the different ways to try to avoid the underfitting and overfitting. How do you determine the number of trees of the model? In this case, I fix it. Again, random forest, because we are focusing random forest. There are a lot of different type of classifiers. You can optimize. You can optimize in Google Earth Engine, or you can optimize in pure Python. And the thing that you need to do is have a range of number of trees, and split your training data in two, one for training and one for measure the accuracy that you get for the different number of trees, and select the best one. This is one option. And once you have the number of trees, you fix that number of trees as I did it in my script, and then use all your training samples to train in the classifier, and test in the other set that didn't see the classifier in the training step. You can do that in Google Earth Engine, or you can, if you have your data in a local, you can do that because it's faster, I can say. It's faster to optimize the classifier in a local way. You can use Python or your programming language, MATLAB or whatever, and optimize your classifier, and later fix the parameter in Google Earth Engine. Michael asked me, in case of undertaking a classification task on a larger region, let's say Wall Street, getting ground truth data might be impossible. So can you use one Google Earth Pro to generate training samples and convert it into feature collection and use it for training and test? Google Earth Pro. I never used Google Earth Pro before, so maybe you telling me that you are photo interpretation the images using Google Earth Pro or something like that. Yes, you can do that in that way. The problem to scale to big data. The problem to scale the data in big data is that one. If you have samples from a specific region and you wanted to produce global maps, you cannot do that unless your classification is very, very easy. For these reasons, for instance, there are not land cover maps in Africa at some point. Nowadays, you can get dynamic wall. Dynamic wall, which is in Google Earth Engine, is a near real-time at 10 meters spatial resolution over all the wall. In that case, they did it a big effort to get samples from different parts of the wall and then produce the classification map. If you wanted to create global scales maps, you need to have samples from the global for all the wall. I mean, also because the reflectance values from one acquisition to the other in the same area are different. Time to time, there are problems when you are using temporal series because a lot of people try to predict 5 years before, try to train in 5 years before and predict 10 years later or something like that. And then that is a problem. But yes, you need to use, you need to get at least few samples from different parts of the world. Can we get a link to the GE file you have used? Of course, yes. I'm going to save and I'm going to copy and paste the link in the chat. You can use it and you can play with it, sure. Suppose you want to make a dynamic prediction, let's say a case of land change detection. How can this be done in Google Earth Engine? Dynamic prediction is different than land change detection, at least for me. So if you wanted to use Google Earth Engine in order to do a land change detection, my suggestion is try to predict in one specific year, and then in the other year that you wanted to evaluate the different chains. For instance, if you wanted to analyze how Nairobi changed in the last 5 years, you can make a classification, the urban classification using the urban class and other classes. And then you can get a classification map from 5 years ago. And you have a classification map that is telling you where are the city and that type of thing. And then you can classify the area as the same area nowadays, and then you can subtract both of them, and then you can see the changes of the Nairobi city from 5 years ago till now. Dynamic prediction is a bit more complicated in that way, because to me, dynamic predictions is more like reinforcement learning. If you wanted to know how to predict dynamic variables as can be vegetation and analyze the change of them, is kind of the same than the same examples that I use it with the urban area in Nairobi, for instance. You predict in a specific year, you predict in some years before, and you subtract, and you can see how the crops change. Another thing is that you wanted to use the temporal information to predict, which is totally different. And I don't know, Nicholas, if you mean that.
Yes, I'm okay. That is
If you
what.
mean that,
Yes.
if you wanted to use temporal information, temporal series, you hello?
Yes.
Hi? Ah, okay. Because I lost the connection at some point.
Yes. Yes. Yes.
um, if you wanted to use image collection, you prepare your image collection, and once you have your image collection, remember that at the beginning of the script, I use the function first to transform the image collection to image. Then in that case, you should use the function toBands. That means an image collection is transformed to image. And you can use that image. You are going to have an image with a lot of bands. That is all the bands that you have in your image collection. And then you can use it that to classify and to predict. More questions?
Okay. Anyone with any question, you can open your mic or you can type on the chat.
Sure.
Then Emma is here to.
I will answer, yes.
Yeah. Yes.
Hope you like the talk.
You can see some claps here.
Yeah, that is the
Yeah,
people
so
didn't sleep, was not too bored.
yeah,
Yes. Uh,
that means they were listening. They were listening.
Yeah.
Yes, yes, yes.
yes. Nicholas. Uh,
Yes, Michael.
okay. For my side, I'm very okay. All my questions have been answered well, and the presentation was so nice and educative. I've learned a lot about machine learning in Google Earth Engine. Yeah, thank you so much.
Thank you to you. And I mean, thank you.
Yes.
Thank you,
Yes.
Luis.
Yes. Yes. Yeah.
uh, can contact at some point again if you wanted more detail or something like that, and we can prepare other talk more detail if you wanted and you need it. It's not a problem.
Okay.
Yes.
Okay. Thank you. Yes.
So Serena is
Would you like
saying,
the presentation? Wait a second, I'm going to share, because someone asked about the presentation, so I'm going to share the presentation also in the chat. If I know how to do it now. I think here, yeah. And then you can have also the presentation. Yeah. Here are the slides. So you can. The session offline, what means? I don't know if I didn't record the session, so I don't know if someone record or not. Any other resource of machine learning? You have a wall in internet, YouTube. You have also a lot of medium descriptions of machine learning. I mean, if you are really, really interested, you have a lot. And making a fast search from Google, you can find a lot of information.
Yes. So on the recording of the session, so the session is being recorded.
Because someone asked for that.
Yeah.
James Muiru asked for the recording.
We'll provide that after the session.
Provide him the session. Have done machine learning with Python in Colab. Has seen we can also use JavaScript, but with limited features, as you say. Is there any needed of learning JavaScript for same? Also, you can have a lot of information. I didn't say, I'm going to put in the chat also, because you have here, where is that? Here. You have here, this link, is the user guide of Google Earth Engine. And if you research there, you can find a lot of information in Python. And also you can find in this is really useful, Google Earth Engine. I need to research for that. Wait a second. Tutorials. Let me see if it is this one. No, it's not this one. A second, and I can look for that. This one. iPhone web. So you have here a lot of tutorials which are really nice in JavaScript and in Python. So you have the two options. You can see that you have in the menu, you can find in the left menu JavaScript tutorials and Python tutorials. So you can see how to use, and also I think that the tutorial of detecting chains in Sentinel-1 is in Colab, I think. So you can have a lot of information. And for instance, one of the JavaScript tutorials was done by me. you can see that is the JavaScript tutorial. The Highest RFM tutorial was done by me and some colleagues because it's a data set without clouds. We produce a Landsat temporal series free of clouds. So yeah. And you can find a lot of information there, also in Python and in Colab. The tutorials are in Colab, the Python tutorials. I don't know if there is more questions.
I think we are learning from the best. If some of the tutorials we learn from are written by our speakers, this couldn't be very bad.
Thank you. I like that the people like the talks.
Yeah, they really like it. So
I was
this is
afraid
really
because I have very Spanish accent, so I'm not sure if
it
if
was
my
really
accent
nice.
was good.
No, it was really nice, really nice. You didn't make us lost.
Okay, thank you.
So for me, I am very, very much grateful. What I would say is that as a community, we are really happy to have you here, Emma. My co-organizer is Christopher and Michael Wafula. They are here. They can say a word. Then we can even hear a word from one of our members or two of them about our presentation and even in the previous sessions, because we have been having a series of these kind of sessions. So you members, you have been here learning with us. You can say something about the community, how the progress has been. So for this time, I'm going to welcome Michael Wafula, Christopher, then we'll be having 2 or 3 members. Anyone willing to say something, you are welcome to have a chat with us. So Michael, please.
Yes. Thank you so much, Nicholas, and our speaker Emma for that nice presentation. I'm Wafula Michael Wekesa, just like Nicholas has mentioned. I'm also um, I'm also part of the organizing team. That is um, Google Earth Engine Nairobi, and we are very interested in Google Earth Engine and remote sensing. That is for processing remote sensing dataset, and that's why we have these sessions. And this one has been a nice session on machine learning. We thank you so much, Emma, for that nice presentation. It's been educative and lively. Yeah. So otherwise, on my side, I don't have much to say. Just to welcome the members for the.
Chris.
Yeah. Hello, everyone.
Hi.
Yeah.
Hi.
So I'm Christopher, a data scientist here in Kenya. Also a G developer. We are privileged today to have to learn how we can leverage ML machine learning in Google Earth Engine. This session I think was the one of the best because most of the guys now were really going into Python way, the scikit-learn. Now if you can do it now in Google Earth Engine, then it will be easier for those guys who are on the cloud and JavaScript part. So thank you so much, Emma. We are happy for the session. It was a great one. So I don't have much to say. So thank you so much. Have a lovely weekend.
Thank you to you for inviting me, all of
So
you. And thank you, Nicolas. We had some problems to fix this session, so you were very patient. So thank you very much.
yeah, I remember we have been talking late night, talking to fix all these things. But
Yeah, was
yeah,
sorry for that.
it's fully understandable. So maybe you can hear from our members. Maureen Gitao. You can open your mic and then say something. All right. Lois is here. Lois, you can say something. You have been with us since the time we started. Okay. Anyone with anything to say to yes members of the community? James?